In this lesson, we're going to do some calculations with equilibrium problems using a tool called ice tables. They're called ice tables because they're cool. So what we will do is we'll explain what an ice table is, how you can use it, then we'll work two homework problems from Wiley, 15-26 and 15-29. So I want to say before we get going that this method of solving problems is completely optional. You do not have to use ice tables. In fact, I noticed that the Wiley reading goes to great lengths to not use ice tables, to the point where I think the problem is more difficult to solve without it. But anyway, I just want to make this tool available to you. If it helps, use it. If it doesn't help, then solve the problem, whichever method works best for you. I think that the assigned problems are easier to solve if you use an ice table than if you don't. Try it both ways and use the method that works for you. It's up to you. So what the ice table is, it's a bookkeeping device. It helps you keep track of the amounts of reactants and products in an equilibrium reaction. And that's the most challenging aspect of these problems, of keeping track of how much reactant and product you have. You can figure out initial equilibrium amounts and the amounts that your reactants and products change. Let's look at an ice table. It's called ice because there's three parts. You're going to write ICE down the side. I stands for initial. It's the amount of material you have when you start. C is the change. When a reaction progresses, some reactants are going to go away and products are formed. The equilibrium amounts are the amounts you have when the reaction is at equilibrium and the forward and the reverse reaction rates are equal. So when you set up an ice table, the amount of reactants and products at the beginning of the reaction, and you'll get that information from the problem. So just like we said, reactants will go away, products will form. You put that in the change row. Now this is easy to calculate. Initial plus the change equals the equilibrium. This will tell you how much is left after the reaction reaches equilibrium. So when you set up these problems, you will have an equilibrium expression and your math will break down to one equation and one unknown, and it just takes a little bit of algebra to solve this equation and find what they're looking for. There will be some math, just so you know that's coming, but if you can solve for X, the math will be fine. So let's start with an example. What I said might not make a lot of sense now, but it definitely will when we see it in an example. So in 1526, here's one of the problems. We have a reaction of nitrogen and hydrogen going to ammonia. 0.9 moles of nitrogen, 0.8 moles of hydrogen mixed in a 1 liter container. This helps us a lot because if our container is 1 liter, then our moles equals molarity. We're going to put molarity values into our ice table. At equilibrium, it's found that the ammonia concentration is 0.30. So they want to know what are the concentrations of nitrogen and hydrogen. The ice table will help us figure out what we have, what changes, and eventually what we have at equilibrium. So you might want to pause the video, write this information down as I apply it to the ice table. Okay, there's our reaction. There's our I, C, and E. So the problem said initially we have 0.9 moles of nitrogen. So that goes under nitrogen in the initial row. We have 0.8 moles of hydrogen. Now they don't say anything about ammonia, but they say initially we have just reactants. So the amount of ammonia is 0. For the change, We know some nitrogen goes away, but we don't know how much. So we're going to say minus X. Based on the equation, if 1 mole of nitrogen goes away, then 3 moles of hydrogen will. So under the hydrogen column, we're going to say minus 3X. Then for the ammonia, we're going to say plus 2X. We add up together the initial and the change. That gives us the equilibrium values. And we've now filled up our ice table. Okay, now what? We might be stuck, except if we look at our given information, they tell us that the equilibrium concentration of ammonia is 0.3 molar. That means that 2x equals 0.3. We can now solve for x and get numeric values for all our equilibrium concentrations. Let's do that. Okay, if 2x equals 0.3, x equals 0.15. Finding the ammonia concentration, the nitrogen concentration, 0.9 minus x, 0.15, 0.75. For the hydrogen, 0.8 minus 3 times 0.15, that's 0.35. And we're done. The ammonia is 0.3, that's given. Hydrogen is 0.35, nitrogen 0.75. The ice table helped us keep track of our initial and our change and allowed us to find the equilibrium values. Now let's look at 15-29. The problem says at the start of this reaction we have carbon monoxide, chlorine. Does anybody know what COCl2 is? That's phosgene. That's a poison gas. It's kind of a side note. They give us that the carbon monoxide concentration 0.64 molar, the chlorine concentration 0.435 molar. At equilibrium, they say that 11% of the carbon monoxide has reacted. What are the carbon monoxide, chlorine, and phosgene concentrations at equilibrium, and what is the equilibrium constant? The main thing we want to do is organize our information. The ice table allows us to do that. There's our reaction, there's our I, C, and E. So they say at the start of the reaction. Well, I'm going to put that under initial. Carbon monoxide, 0.640 molar. Chlorine, 0.435. And if the reaction is just starting, we have no phosgene. 11% of the carbon monoxide has reacted. That is our change. 0.110 times 0.64, 0.0704 molar. That's how much goes away. We're not putting an X like we did before because it tells us how much goes away. Minus 0.0704. Now the stoichiometric coefficients are all 1. So if 0.0704 molarity of carbon monoxide goes away, the same amount of chlorine goes away, and the same amount of phosgene forms. Our equilibrium is our initial plus our change. So we just add all of our columns. That gets us 0.570 molar for carbon monoxide, 0.365 molar for chlorine, 0.0704 molar for our phosgene. There are our equilibrium amounts. The next part of the problem, we'll find our equilibrium constant. So all we need to do is plug into the equilibrium expression, products over reactants, raised to the stoichiometric coefficient, don't include solids or liquids. Well, these are all gases. So our equilibrium expression, the product, phosgene, divided by carbon monoxide and chlorine, we've got numbers. We plug those in. Go ahead and do the math, check mine. We get a K value of 0.338. So really, for equilibrium problems, the most challenging part is keeping track of your amounts of reactants and products. The ICE table does a good job at that. Just consider it another method to help you solve problems. If it works, use it. If it doesn't work, you don't have to. As always, contact your course mentors if you have questions. We are here to enable your success. Here's our contact information once again. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.